All right, guys. This is officially the last lecture. So I think I just want to clean up a few things, concrete things from last time, make some, and then step back and make a few more general remarks. I would like to give maybe another 3 lectures on some new ideas. I see. Okay. We just wrote down at the end of last time just what the explicit formula is for an all-loop recursion relation, an extension of the BCFW recursion relations to all-loop order. This is, again, by itself something that you could sort of write down as sort of thinking about it and finding the various ingredients that go into it, in particular the idea you should think about loops as hidden entanglement and so on. This was all very much suggested by and motivated by thinking about the Grassmannian geometry and amplitahedra and so on and so forth. But the recursion relation is something you can just write down by itself. Let me just write it down. All lug, that's something. All loop recursion. And I just want to just sketch one example at least and make some comments. So this recursion relation for the superamplitude planar n equals 4. J, of course. And then there's the new things that we discussed having to do with loops and this GL2 integration and the forward limit and so on. Oh, sorry, this is loop loader L left, L left, and L right. But now. Okay, so where all these funny hatted these intersections are, n hat j is where the line n minus 1 n intersects the plane jj plus 1 1. ij is where jj plus 1 intersects n minus 1 n hat. And a hat is where the line ab intersects n minus n1. Again, that's responsible for going to the forward limit, and then n hat AB is where the line n minus 1n intersects AB1. Okay, and again, this is what we get from imagining doing the BCFW shift in momentum twisters, where Zn goes to Zn plus some Z, Zn minus 1. Okay, and I remind you also that this first term is taking into account all the tree level, all the factorizations where just some particle goes on shell in the middle, some tree-like factorization, where of course now we can have some loops on the left and the right, so the total number of loops are adding up to the total L. And this term is the sort of seed of the loops is the forward limit, where an internal loop propagator goes on shell, and you and we identify the momenta and we sum over everything. Okay, so this, as I mentioned, it's a completely concrete formula. The GL2 integration is done on a residue. Everything is algebraic, and you can just shove it on a computer and get the answer. It's just a matter of how long you want to wait to get the answer. As I've stressed several times, the answer, the data that exists about n equals 4, forget about words, interpretation, blah, blah. The actual facts are sitting on Jake Bergeli's laptop, okay? And if you want to know the answer, 2 loops, even 3 loops, up to any multiplicity, you want the answer is there. Starting at 4 loops, you might have to ask nicely. And in principle, it's there, and it's recursively doable. Just as an example, I won't do it in detail, but just so we have an idea of what it looks like. In the simplest case at loops, if we do k equals 0, so for MHV integrands, this formula collapses a lot. These terms aren't there. There's no factorization at all for k equals 0. We only get this forward limit term. Furthermore, what we get here, if I put k equals 0, is just the k equals 1, which is that simple tree amplitude that we knew the answer for. The sum of 1 I plus 1 jj plus 1 is one of many triangulations for it. And so the result of doing this recursion is the following very simple formula. All I have to do is sum over all j. In fact, you see, I get mn as mn minus 1 plus a forward limit term. Okay? And then, so recursively, mn minus 1 is mn minus 2 plus a forward limit term, and so on. So the whole thing just turns into a single sum, a sum over j of ab jj plus 1, 1. This is just this n minus 1, abn minus n1. That's just this abn minus 1 n term, where I successively, and I'm decreasing n when I do this recursion. And now instead, what I have to do is compute, put in the NMHV tree amplitude here, and I'll give the representation for that, which is the simplest one that I would get if I was shifting a hat, if I was shifting a, actually. So this just gives me this formula, sum over j and k. And I have to do the GL2 integral of this guy. And we can almost do this in our head. By now, we can almost do it in our head. As usual, all of the eta integrations are just going to give me something trivial. Okay, so I'll just do the eta integrals. I get some numerator, but I don't even have to work it out explicitly, because we just work out what the denominators are, and then we'll see what the numerator has to be just by weights. Okay, so what are the interesting possible denominators I could have? Well, from each one of these R invariants, from each one of these objects, I can get numerators that look like, for example, I can get AB jj plus 1. So that's a nice physical pole. On this side, I could get AB kk plus 1. And then I can get the other ones. For example, I can get things where A and B are alone, like B jj plus 1, 1. Okay? I can also get jj plus 1, 1a. Sorry, I can also get j plus 1, 1ab, and also j, 1ab. Okay, so let's look at, so let's write down all the ones that involve just ab together. And then on the other side, I'll have ab 1k, ab 1k plus 1. And then I'll have some other things where a and b are alone. Okay? And those are exactly the things that we do on the GL2 integral. Right? These things are GL2 invariant. Those are exactly the things that we do on the GL2 integral. And as happened in our previous examples, they're just going to give us some AB independent thing. We're going to get some function of the line AB. A and B independent thing, but a function just of the line AB. Okay? But what function of the line of AB can it be? we have these 6 factors downstairs. We have to have a total weight upstairs of 2 in order for this whole thing to have correct weights in AB. And so the result of doing the GL2 integration is simply, I'll just write down the answer. This is 1 over AB I plus 1, AB 1I, just these factors that we had already, and then AB, JJ plus 1, 1J plus 1, and AB 1, KK plus 1, AB 1K, AB 1K plus 1. And upstairs, I get a factor of AB and 1 II plus 1 intersect 1 JJ plus 1, all squared. So see, I have to have something that has weight 4 in the 1s because there's 4 1s downstairs. Weight 2, J and K. And furthermore, it's exactly these planes that are showing up in the problem. 1 JJ plus 1, 1 KK plus 1, and those are exactly the planes that I'm seeing here. AB, 1 JJ plus 1 intersect 1 KK plus 1 squared. Explicitly, this numerator factor I can also write as A, 1 JJ plus 1, B, 1 KK plus 1 minus A, 1 KK plus 1, B, 1 JJ plus 1, if you like. Okay, so this is just writing explicitly what the intersection AB, what the intersection of the planes 1I JJ plus 1, 1 KK plus 1 with AB looks like. Okay, so that's what you directly get from the recursion relation. We sometimes denote it by a picture like this, where you have 1 JJ plus 1 and KK plus 1. So that tells you all the poles that you see in the answer. 1J, AB 1J, AB JJ plus 1, AB 1J plus 1, and so on. And this little wiggly line denotes that there's a numerator there upstairs that looks like the intersection of those planes. 1I plus 1, 1 JJ plus 1 squared. Sum over J and K. And I drew this picture just so I have an excuse to tell you what it's called. It's called the Kermit expansion. And that's because this kind of looks a little bit like Kermit the Frog. Okay? And so when you do loop level BCFW, you see Kermits all over the place. Kermits at one loop, Kermits at higher loops. So this is the answer you get from the recursion relation directly. Okay? So you get and notice that it has 2 physical poles, AB JJ plus 1 and AB KK plus 1. Those are the physical poles, and it has a stack of spurious poles. And of course, they're supposed to all cancel out in the sum, as we're always used to seeing. Now, here's a little bit of, again, a little bit of magic. If all you ever knew were recursion relations, nothing else, you would get this answer. It looks sort of nice and simple, that the one loop amplitude for MHV amplitude is so simple, it's just a single term, like essentially sum of a single term like this. But if I look at the form that I want to integrate, so the form would be d4ZA, d4ZB, modulo GL2. So the form for k equals 0 in AB would be this times this amplitude that we just talked about, that we just computed for Mn and k equals 0. Okay, but it looks like some kind of sort of complicated 4 form. However, for each one of these pieces, if you expand, let's say ZA in the way that's natural, suggested by the problem, if you expand ZA as Z1 plus XI plus XJ, ZJ plus XJ plus 1, ZJ plus 1, and ZB as also Z1 plus XK, ZK plus XK plus 1, ZK plus 1, then to your delight, you'll discover, so this is the sum. Again, I'm summing you'll discover that omega is the sum over j and k of some omega jk. But each one of these pieces, if you put this in, you'll discover that omega jk is actually just d log xj, d log xj plus 1, d log xk, d log xk plus 1. It's remarkable. This kind of complicated thing with 6 poles downstairs and this interesting numerator squared is actually a d log form. And this is this is a more general version of the surprise that we saw very early on when we drew the massless box diagram. And we noticed the massless box diagram was d log, d log, d log, d log, right? Was also for d log. So there's this thing hiding under our noses in the structure of perturbation theory that's begging for this connection to a geometry just in what these integrands look like. And that tells us finally that that we can write the actual form, since we can just solve for x, for these x's in terms of a and b in the way that's by now familiar. So we can actually say that omega for k equals 0 and n is just a sum over j and k d log ab 1I over ab jj plus 1 Okay, so that's what our form is. And finally, you'll remember, I hope, from maybe 4 lectures ago, that that's exactly what we got for the triangulation of the m equals 2 amplituhedron. So when we looked at remember, at one loop, it just so happens that for good reasons, that the loop level m equals 4 amplituhedron is the same as the tree level m equals 2 amplituhedron. The loop level m equals 4 amplituhedron for k equals 0 is the same as the tree level m equals 2 amplituhedron for k equals 2. And we triangulated the amplituhedron for k equals 2 for any k for m equals 2. And we wrote down the canonical form. And we wrote it as y instead of ab, but that's what the connection is, right? But this was precisely the triangulation that we talked about. And remember, this was associated with that triangulation where we found that there was a sign flip pattern for involving y, and the sign flips occurred at the locations j and k. Okay, so this is really directly tied to that understanding of the m equals 2 amplituhedron. So after all of that work, we can derive these things from the recursion relations, as I said. That's the just like at tree level, BCFW gives us this connection to this proper connection to a field theory. Even at tree level, we get the sum of all these different terms, which field theory tells us to glue together in order to make the answer local and unitary, right? Then we discover that we can interpret those terms as actually triangulating the amplituhedron. And the amplituhedron tells us where locality and unitarity come from. It's not the desire to make the answer local and unitary. That's just what we get. And in fact, at tree level, there's something quite canonical about BCFW, because somehow, we still don't understand why, but somehow the triangulations of the amplituhedron, in terms of at least those triangulations that can be interpreted as images of cells of the positive Grassmannian, they're very rigid. All the triangulations we found, they all have the same number of terms, for example. If you want to do like 8-point n squared MHV amplitudes, they all have 20 terms. Every way of doing them has 20 terms. But we can't get all of them from BCFW. So it's not true that BCFW exhausts every way of triangulating the amplituhedron, even at tree level. But BCFW does give you that number 20. Okay? So there is something canonical and good about the BCFW triangulations at tree level. At loop level, it's much less true. Okay? At one loop, it's still pretty okay. At 2 loops and higher, this recursion does produce for you, and I don't have time to explain it, but we can really go back to the whole thing, just like we talked about what the tree level diagrams look like and what the BCFW diagrams look like in momentum twistor space. You can go further and talk about what this entire loop level recursion looks like in momentum twistor space. And there's a cousin of on-shell diagrams that now includes this AB business in an interesting way, and that produces for you those C and the D matrices that we're supposed to associate with the amplituhedron. So that whole story extends to this recursion. It's very concrete. There's a totally concrete diagrammatical way of carrying out this on-shell recursion, and that diagrammatic way produces for you matrices, C and D matrices. Okay? We know that the C matrices that are produced in this way are positive. Okay, so that's the connect. We have not yet proven that the D matrices that we produce in this way are positive, that there's some correct way of choosing the sign for the edge variable so that the D matrix is positive. It's true in all the examples so far, but this is one of many, many open problems, even totally within this business, to completely establish the connection between the amplituhedron and the on-shell way of doing BCFW, especially in momentum twistor space. Okay, but one reason I'm emphasizing all of this is to point out something kind of fascinating, which is that, you see, the question of how have recursion relations computed an MHV amplitude at k equals 0? We've computed an MHV amplitude at k equals 0 by talking about, let's say, NMHV amplitudes, tree amplitudes at k equals 1. So we exit the world of k equals 0 objects, and now we're talking about k equals 1. Let's say I want to do 2-loop MHV amplitudes. Then let's say I want the 2-loop 4-point MHV amplitude, which is a very simple object. We finally got it. Remember, we got the sum of two little boxes, like two little dominoes like that. Okay, in order to get that sucker from this picture, we've got to go all the way back to 8-point n-squared MHV trees, which is not unreasonable. It's sitting there inside. We know if we do unitarity cuts, we can see something as big as the 8-point n-squared MHV amplitude sitting there in trees, and we take these various forward limits. But this is a pretty complicated object. You do GL2, you do all these things, and you get not a very long expression, but still a pretty reasonably complicated expression. All the spurious poles cancel, and you end up getting the sum of those two little terms. But remember, the problem that defined the 2-loop 4-point amplitude, in fact, the loop amplitude for any k, is defined as a geometry problem in that k. It makes no reference to higher k. It makes no reference to anything else. And associated with that, the triangulations that we found were very simple. They didn't look anything like what you get actually from the BCFW from this method. So there's already some indication that while it's true that we have this connection, while it's true we have the picture I erased of the forward limit and the factorizations, those are the important singularities of amplitudes at loop orders. For n equals 4 superpositing mills, they completely determine the amplitude. It's true that those singularities arise as a consequence of the amplituhedron geometry, but they're quite derivative things. They're true and you can derive them, but they're quite derivative things, and the geometry cares about other things. So we still don't understand all the things that it cares about, but it's framed in a different language. It cares about other things, and even computationally, the sort of nicest ways of triangulating the geometry at tree level have something to do with BCFW. At loop level, do not seem to. Okay, and it's a very nice open problem to figure out how to correctly think about this geometry. In particular, I already highlighted the 4-point problem to all loop orders. Solving the 4-point problem to all loop orders is this little high school geometry problem involving sets of points in the upper quadrant satisfying these mutual positivity conditions. Okay? Nothing in that problem makes reference to y or k or any of these things. It's just this little simple geometry problem. And of course, it's not easy to solve, but if there's some idea for how to crack that problem to all loop order, understand some combinatorial structure controlling it, understand any analog of the things that we've understood about positivity for the positive Riemannian, for this very simplest case involving mutual positivity, then I suspect that would be that would go far. That would give some perhaps beginning of a clue for extending these ideas beyond perturbation theory to saying something non-perturbative. If we can understand that very simple problem, concretely and explicitly to all loop order. Okay, so just to summarize this part of the story then, so this gives you a concrete formula for getting the answer to all loop orders. At tree level, we can understand all the pieces as coming from particular triangulations of the amplitahedron. At loop level, it's also true that the pieces are triangulations of the loop level amplitahedron, but it gets more complicated. I mean, it gets more complicated to see that it's true, and it does not, at least at the moment, appear to be the sort of natural way of thinking about what the amplitahedron is at loop level. So again, the facts of locality and unitarity, which are where the poles are. At tree level, where the poles are involving the intermediate particle. At loop level, the fact that we get poles when one of the internal loop momenta go on shell, right? So those are the statements of locality, where the poles are. The statements of unitarity is what happens on those poles, that you factorize, and that you have the correct matching between the single cut and the forward limit of the lower point amplitude. Again, that's where supersymmetry snuck into this business, because understanding that forward limit in generic theories with no supersymmetry is very delicate. But in supersymmetric theories, it is okay. That's why we can focus just on the simplest, lowest codimension, first singularities, just these simple poles. And there's a statement about what the factorizations look like on those poles. And that's locality and unitarity. And because of the sort of magical fact that n equals 4 super Yang-Mills is dual conformal invariant, we can use that to tell us about the absence of poles at infinity, and use that, leverage that information to recursively construct the integrand to all loop orders. Okay, so in principle, you could say all of that without knowing anything about geometry or amplitahedra or anything else. But the interpretation, that now there's a very beautiful interpretation that the pieces of this recursion are triangulating an object. And furthermore, already all the pieces and everything else that we can get besides associated with all the cells of the positive Grassmannian are kinematically associated with all the sort of Yangian invariants of n equals 4 super Yang-Mills for SL 4/4, SL M/M Yangian symmetry. But again, just from that point of view, you have no idea why you're putting these objects together in the particular way you're putting together as dictated by physics. And it's the amplitahedral geometry itself that tells you have to be put together in that way. And completely independent of any triangulation, it's the geometry that tells you that on the boundaries you have this kind of factorization, which we interpret where the boundaries are, and that on the boundaries we have the kind of factorization that we interpret as unitarity. So in a very concrete sense, locality and unitarity come out. Okay. Now, I alluded to it a few times, and we actually talked about it in some detail before we got to fancier things in Grassmannians already with NMHV amplitudes and cyclic polytopes. But I just want to write down one more time what the sort of final, at least one of the, or closer to a final step in this program was to see this positive geometry and the amplitahedron in kinematic space. So for the past 3 weeks, we've been thinking about the amplitahedron in the language that it's some object that lives inside GK k plus 4, GK k plus m, and there's this funny business that the z's are external data, but they're not just 4 vectors; they're 4 plus k vectors, and the extra k components are where the supersymmetry or the helicity information lives, and so on. But let me just remind you again, since we've said it a few times, that we've since understood how to talk about everything directly in the space where the amplitudes live. And I'll just draw this picture again. So the spaces, so we have this kinematic space. Draw a little bigger. So we have this kinematic space of the momentum twistor Z and a bunch of lines AB1 through ABL. So this is just P3. Okay, just the, or let me, actually R4. They're all 4 vectors. So these are points and these are vectors. And these are 2 planes in 4 dimensions. Okay? So this is the kinematic space. That's what things depend on. And the whole story is that the amplitude is a form, 4 times k plus L form. So we're looking for a 4 times k plus L form in this space. And it is determined by the following property. First, there's a nice positive region in this space. And the positive region is defined by asking for all the z's that the I plus 1, jj plus 1s are positive. We saw where that came from. Otherwise, from positivity conditions, but here we're just imposing it. We ask that for every loop, the AB I plus 1s are positive, and the loops are mutually positive. And in this space, I can look at the following object. If I look at the first, if I look, since I have the ordering, it's natural to look at the following simplices. So these would be tetrahedra with vertices I plus 1, jj plus 1. If I sum over all of these things, as we've discussed many times, yes?
I just wanted to ask, can you clarify the picture a little bit? What's the plane? What's the...
Yeah, I'm going to say what the, so we're going to get, forget about the plane forget about the plane for now, okay? Yeah. Well, I won't erase it. Forget about the plane for now. So this space is obvious, right? Just the space of n 4 vectors, right? And L 2 planes in 4 dimensions. Now we're going to ask a question in this space. Okay? To set up the question, first in this space, there's a nice region. Okay? There's a positive region. So we'll first talk about the positive region in this space. The positive region is defined by a bunch of essentially saying that if this was 2-dimensional, which we'll also come to in a second, it's sort of since the things are ordered, it's natural to talk about the lines 1, 2, 2, 3, 3, 4, and so on, right? So it's very natural to look at this set of objects, and you'll notice that set of, so first it's natural to ask for them all to wind around the origin in the same way. Okay, so that's demanding that all the I plus 1s are positive. Now the 4-dimensional analog of this is to ask for all the I plus 1, jj plus 1s to be positive. Okay, so that's the first thing. That's sort of asking for all these tetrahedra to be oriented the same way. Okay? And this is asking for the same thing when you project through any one of these lines. So if you project through any of these 2 planes, we go from 4 dimensions to 2 dimensions. And then we're just asking under the projection that all of the 2-dimensional vectors that we get now all wind around the same way. Okay? So this is just asking for everyone to wind around in the same direction. Okay, so that's what these conditions are imposing. And having found something that they're all winding around one way, now we're just going to ask them to wind around a certain amount. Okay, and so the first thing to do is to look at this set of simplices. We've mentioned a few times that if I take the boundary of this thing, it's 0. If I take the boundary of this guy, it cancels telescopically in the sum. So this is a collection of 3-dimensional simplices. Okay, it's a collection of 3-dimensional simplices that has no boundary. It's topologically an S3, and you can ask this S3 to wind around the origin some number of times to have an S3s winding around the origin. Okay, so this guy should have some winding number, which turns out to be, for any k plus 3 over 2, the floor of that, choose 2. Now, I'm not explaining where that comes from. Okay, but I'm claiming that. But this is meant to be the answer to the question. Back in terms of y's, let's say you did fix your z external data, and let's say you projected through y. You move y around. The z's are fixed. You move y in the amplitahedron, and you project through y. When you project through y, you get four-dimensional data, right? And now the claim is that y is in the amplitahedron if and only if that four-dimensional data satisfies these conditions. Yes?
You said it was the first two.
Yeah.
The third one, was that positivity?
The third one you can think about as like projecting all the way down to 0 dimensions, if you like. So they're all sort of mutually positive with respect to each other. So this is a positive winding in the four-dimensional sense, in the two-dimensional sense, and in the zero-dimensional sense, whatever that means exactly. Okay? But that's okay. So this is a non-trivial claim. I have not explained where this comes from. I'll give a tiny bit of intuition for it in a second. And at loop level, if I now look at the sum over I, for the I plus 1s, which are what I get after projecting through any AB. Okay? So if I project through the AB, I have two-dimensional data. So this is the natural thing, the more intuitive thing, literally winding. This has winding number k plus 1 over 2. Okay.
Exact, or is that a limit?
No, it's exact. They have to be exactly equal to this. And in a precise sense, this is the maximum winding they can have as well. I'm not explaining any of these things, but I'll give some intuition for why being in the amplitahedron has anything to do with winding numbers in a second. Okay, okay, so this is what the positive region looks like. Now, what does this subspace look like? So we talked about this a few times already too. This is a 4K dimensional subspace. All the points on this subspace look like ZAI is some starting point, Z star AI, plus Y alpha I, some delta alpha A, delta star alpha A, where, so this subspace is associated with this, giving this data, what the starting point is. So giving this 4 by n and k by n data, which I can group together into this 4 plus k by n matrix. Remember that 4 plus k by n matrix is exactly what in the amplitahedron language we're calling our external data. Okay? But now instead of thinking about it as fixed external data, this is just picking out subspace in the kinematic space. And we have to demand that this 4 plus k by n matrix is positive in the positive Grassmannian sense, that all the minors are positive. Okay, so this defines, so there's a positive region. Okay, what I'm trying to explain here is where all of this amplitahedral geometry can live when all I have is kinematic space, right? I don't have any fixed data, I just have this stupid kinematic space. So where the heck is all this geometry going to live? And the answer is that first, in the kinematic space is this top dimensional region that winds around correctly, positively winding and winds around correctly. And secondly, if you now intersect that region with some interesting, I mean, this is just some simple affine subspace. I'm just translating a point. I start with a point and I translate in some direction. Some very simple linear subspace in the kinematic space. But if I intersect that linear subspace with this region P, I get a very fancy geometry. Okay? Notice that what's moving me around on this subspace has exactly dimension 4 times k. So that's exactly, the little y's are mapped to the little y the y variables we think about in the amplitahedron. Okay, but now we're seeing the amplitahedron directly in kinematic space. So you fix a subspace. The intersection of this subspace with P is the amplitahedron. And so finally, what fixes the amplitude? what fixes the amplitude doesn't live there. The amplitude lives everywhere. It's a form that lives everywhere. Okay? It's not a top form, but it's a form that lives everywhere. However, it's completely fixed by the requirement that no matter which of these subspaces you pull it back to, so if you pull back omega to this subspace, omega becomes the canonical form of the amplitahedron on the subspace. So it's something that lives everywhere, but when you pull it back to the subspace, it becomes the canonical form on the subspace.
So would you, subspace, are you assuming it's real? And,
Everything I'm assuming is real in this picture, yeah. The form lives everywhere and is complex even, but if I pull it back to this real place, it becomes the canonical form with logarithmic singularities on the boundary of the amplitahedron. Okay, so let me just give a little bit of intuition for why this is true. So let's ask. Let's just go back to. I mean, this is a very little bit of intuition, but the intuition for amplitahedron versus winding connection. Let me just go back to y equals c dot z in this picture, but let me just do m equals 2, k equals 2, n equals 4. So this is the sort of simplest case where y is actually just the same as the positive Grassmannian, right? Just a positive G24. And let's remember in this case, I have y12, y23, y34, and y14 are all positive, but y13 and y24 are both negative. But let me just try to draw what do the, let's say I have some configuration of four-dimensional vectors. Y is inside the amplitahedron. Let's just try to draw what it looks like when I project this four-dimensional data through Y. And this is what the answer looks like. So let's say 1, 2, 3, oops. Yeah. So when I project through Y, Y has gone to the origin, okay? And I claim that what it looks like when you're in the amplitahedron is this picture, okay? And let's see why this is true. Well, 1, 2, 2, 3, 3, 4, they're all winding around the same way. So is 1, 4. Okay, so, right? So remember, I have 1, 2, 2, 3, 3, 4 positive. 1, 4 is also positive. Okay? But 1, 3 is negative, right? That's 1, 3 is going oppositely, and 2, 4 is also negative in this picture. Okay? Now, let's contrast that with another situation. See, I could also have another region. So the whole problem is that, as we stressed, what makes all this Grassmannian positivity fancy is that first you can't go to boundaries willy-nilly because these positivities are nonlinear and they have and we have Plücker relations that relate minors to each other. And relatedly, we can't just identify what the codimension 1 boundaries are and just say that we satisfy the inequalities associated with the codimension 1 boundaries. For example, here the codimension 1 boundaries are just when 1, 2, 2, 3, 3, 4, and 1, 4 go to 0. But I can't just say that they're all positive, because that's consistent with 1, 3, and 2, 4 either both being positive or both being negative. Okay? So we can see that algebraically. We also see that here in the picture, that I could also have this picture, 1, 2, 3, 4, and the origin sitting there. Right? This also is exactly the same. 1, 2, 2, 3, 3, 4, and 1, 4 are positive. But in this region, 1, 3 is also positive, and 2, 4 is also positive. So here, y13, y24 are both positive. Here, y13 and y24 are both negative. Okay, and what is the distinction between these two pictures? The distinction is that in this case, tuck, 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 I wind around the origin once. Okay, and in this case, I wind around the origin 0 times. Okay, so this has winding number 1 and winding number 0. And you can also see that in this case, I can't wind around more than once. Okay? So the maximum amount of winding that I can have is just with 4 points. I mean, I just can't make it wind around. If they're all winding around the same way, I can make them wind around more than once. So this is even the maximum winding that it can have. But there's another region with less winding. Right? So you're in the amplituhedron when the projected data winds as much as possible. Okay, and so a sort of a big generalization of that is the picture that we have on this board. Okay, yeah, we didn't get to talking about this in detail, but I just want to remind you that it exists. Now, part of the reason I just want to write it all on one board is to say again now for the third time in this course, just zoom back out to the ultimate goal. The ultimate goal was to find some question to ask in the space where the amplitudes live. Amplitudes don't live in space-time. They live on the boundaries of space-time. Amplitudes depend on on-shell kinematical variables. And so we're trying to ask a question in the space where amplitudes live, whose answer is scattering amplitudes. But this answer can't know ahead of time that there are local interactions in the interior of space-time or that there's some evolution in a Hilbert space that guarantees that the answer is unitary. Okay, so the sort of grand ambition of this whole program that we're just scratching around, and we've been talking about in this course in baby examples, is to find some principles that replace space-time in quantum mechanics. Not that, certainly not that take quantum mechanics for granted and get space to come out. But one step beyond that, to have something which asks some questions whose answer you see has all the features that we normally associate with the existence of a local space-time and some and unitary evolution. Okay, and we see immediately what the sort of magnitude of the challenge is, because if you try to go to the natural places where the amplitudes want to live and ask obvious physical questions there, we don't know what to do, precisely because, as we stressed in the very first class and a few times since, we don't have a notion of time on the boundary. We don't have a notion of locality on the boundary. It's not clear what to do there. That's why it's immediately obvious from the very get-go and from many other points of view besides that we have to do something somewhat more adventurous. And this is an example of what that somewhat more adventurous thing looks like. Okay, so we managed to find a question in kinematic space. What the heck can you do with just n 4 vectors, right? That's our data, n 4 momenta, n null 4 momenta. What the heck can we do in the space of n null 4 momenta? And the answer is just a little bit of extra structure. The presence of this ordering on the external data then gives you enough of a kick to be able to start seeing something. The ordering is associated with positivity. And that's the only thing that entered this story. The only thing that was needed for me to be able to make all these statements in a canonical way was to have this ordering on the external particles. And what's remarkable is that it has enough structure in it to give us objects which satisfy all the rules associated with locality and unitarity without having them put in by hand. Now, as I mentioned a few times, this is kind of, at least at the moment, what the final answer looks like, or the temporarily final answer looks like for n equals 4 super Yang-Mills. Along the way, we saw a number of other things. We saw, well before getting here, we saw that just asking a very simple physical question about on-shell processes, right? Think about what the on-shell think about what on-shell amplitudes are. Begin with the fact that 3-particle amplitudes are completely nailed. And already just asking the question of what natural objects you get when you glue 3-particle amplitudes together to get more complicated on-shell processes, that alone brought to life a number of ideas that we're not normally used to thinking about in high energy physics. So we get associated with any old on-shell diagram as some structure in the Grassmannian. And on the one hand. On the other hand, we can actually represent physical processes as sums of on-shell diagrams in a way that's an alternative to the Feynman diagram picture. The Feynman diagram picture makes manifest locality, right? The locality of the interactions in space, and to some extent unitarity. The on-shell diagrams are making something else manifest. It's not obvious immediately what they're making manifest. You just start playing with them to see what you get. At least for n equals 4, we've learned that they make the Yangian invariance of the theory manifest. This very hidden fact is sort of more obvious in the on-shell diagrams, but other than that, it's not so obvious. Well, that's kind of a big deal for this theory, of course. Other than that, it's not obvious what they are doing. Unlike Feynman diagrams, you're not supposed to just draw all of them and add all of them up or anything like that. They're building blocks. Okay? And so at the moment, that's what we have a picture of the amplitahedron. One way of triangulating the amplitahedron is to break it up into on-shell diagrams. There are many other ways of triangulating the amplitahedron. We don't know what the interpretations of all of them are yet. Okay? And actually, we are still, just purely in this world, we're still missing a completely intrinsic definition of what the canonical form is, or how to compute the canonical form in principle. If you give me some amplitahedron for n equals 10, 15 loops, we do not today know how to just turn that into a problem to feed a computer that algorithmically you know how to spit out the canonical form. Okay? We do know how to do it for k equals 1. We know how to do it for polytopes. For polytopes, I gave you one sort of quite beautiful way of thinking about what the canonical form is for a polytope in terms of the volume of the dual polytope. Okay, so that's really a remarkable connection. And we already saw that if I gave you a polytope, you can triangulate it, or I can triangulate the dual of the polytope, and these give you totally different representations. Of course, they give you totally different representations for what the final answer looks like that make different features of the answer manifest. Okay? But this duality between the polytope and its dual is kind of a big deal in the story of canonical forms. And to me, a holy grail in this subject is to find the analog of this dual for the amplitahedron, which we do not have yet. Okay? So the amplitahedron is kind of a cousin of polytopes in the Grassmannian. It's a generalization of polytopes into the Grassmannian. Polytopes have duals. What is the analog of the dual of the amplitahedron? We don't know. We have lots and lots of circumstantial evidence that it exists. Lots of circumstantial evidence that it exists, but we don't know what it is yet. And that's kind of associated. There's a number of problems that seem to like bump up against this central basic fact that we don't know what the dual of the amplitahedron is. Let me make a very speculative comment, which is that we know that everything that I've told you about the geometry of the amplitahedron, mostly in the y space, never mind this stuff, although of course it all maps, but let's just even think about in ordinary, any of these ways of thinking about what the amplitahedron is. Even though there's nothing in it that looks like gluons in space-time, what it's about is gluons in space-time in the end. In other words, all the properties that the amplitahedron makes manifest are the properties that we normally associate with gluons in space-time. Okay? If there's a dual amplitahedron, it should be making something else manifest. And the speculation is that the dual amplitahedron is making manifest the string description of the physics. Okay? So we know, after all, that there's a gauge string duality. And part of the difficulty in establishing this link is that the worlds where the strings live in the anti-de Sitter space with one extra dimension, and the world where the gluons live on the boundary of the space-time, in our usual way of talking about things, involve completely different redundancies of description. That's the whole point. One of the pieces of magic of this duality is that you're saying the two things are dual that have radically different gauge redundant descriptions. The boundary description has the gauge redundancy, the bulk description has general covariance. These things are all in our heads, and there's some totally invariant thing which matches between the two sides. Okay? So how could you see that these two things are related to each other? And at least one idea is that we're not supposed to take one as more fundamental than the other and derive one from the other. That's the most popular idea. And in that idea, you think that the dual CFT is the most fundamental thing because it's well defined, and then slavishly the bulk will emerge from it. It seems totally unlikely to me that that's how things are actually going to work. It's much more likely that there's some different way of thinking about what the physics is, where neither one of those descriptions is especially fundamental, and we actually see them as limits in some way of a third way of thinking about things. And we have like a gajillion other indications other than what we've seen in this course. All the amazing U-dualities in string theory, all these, the stunning structures that are lying around all over the place, which still 20 years on, we have 25 years on, we have not even a shred of it, really a shred of, maybe a tiny shred, but a little bit more understanding of where they came from than in 1995 when they were first discovered. These are really wild, sort of completely amazing things. The usual attitude about them for a long time has been that, well, the fact that string theory has all these crazy, amazing different dual descriptions, that's just the best we can do. It's some big, giant object, and we can cover corners of it with some description, and then there's another corner that's covered with another dual description. And it's like sort of charts that cover a manifold, and there's not one single chart that covers everything. That could be true. But in this story, we've seen a baby version of all of that. In the story of n equals 4 super Yang-Mills, instead of seeing all the crazy dualities of string theory, we've just seen one tiny corner of it, the infinite Yangian symmetry of n equals 4 super Yang-Mills. The infinite Yangian symmetry of n equals 4 super Yang-Mills is actually a kind of T-duality of string theory. It's a fermionic T-duality of string theory. And so you can ask, for that tiny part of the story, is there some way of talking about physics that's manifestly Yangian invariant? And you'd make all the same complaints about it. No, there can't be. You know, in one chart it looks like a scattering amplitude, another chart it looks like a Wilson loop. You make conformal symmetry manifest or dual conformal symmetry manifest. Never the twain shall meet. You can't talk about both of them at the same time. And yet we've seen that's not true. Here we've seen it is possible to talk about the whole shebang in a way that makes all the symmetries sort of trivially obvious. But the whole point is that this is a description that does not look like standard physics. This is a description that's more alien. It's a little bit more radical, right? We don't see a space-time anywhere. We don't see a Hilbert space anywhere. And instead, we see these strange positive combinatorial objects that somehow have all of the magic in them to produce physics. Okay? And this is not physics in, you know, toy models that have nothing to do with the real world. And leading approximation, as I've stressed many times, this physics describes the actual world out there. Right? These ideas describe the actual world that we see outside. I think that's somehow, that is very, very important. And we should follow and think about what the world is trying to tell us, especially when it brings us into contact with some fascinating mathematical structures that care about things that the world seems to also care about. OK, so let me end by talking about a few open problems in this area. And then I'll just tell you a few of the extra things that I want to talk about in the next number of lectures, the bonus lectures. And this is just it's a smattering of thoughts. There are many, many more things I could say, but just most directly related to things that we've talked about. So some open problems. So sticking close to what we've done already, one question, here we've seen the amplituhedron in momentum twistor space. We saw that everything is sort of very uniform between momentum twistor space and ordinary lambdas and lambda tildes. So surely there should be some kind of amplituhedron for momentum space. Okay, so is there an amplituhedron in momentum space? Lambda tilde space. Actually, very recently, about a couple of months ago, there was a very nice paper proposing a momentum space amplituhedron by Livio Ferro and Tomek Lukowski and their collaborators, Matteo Parisi. And very roughly, it's kind of like what you might expect, that now we have the image of something like y equals c lambda instead of y equals c dot z. But in momentum space, we have lambdas and lambda tildes. So you should also have something like a y tilde is c perp dot some lambda tilde. Okay, so I'm being very, very sketchy, but there is some idea like this that has passed a number of checks for the tree level, at least for the tree level amplitahedron, and loops are still missing. But this sounds like a very, very doable. Well, I think there'll be some interesting conceptual points involved. But one reason I'm highlighting this is because if we can start talking about the amplitahedron in, so this is the y picture. What is the picture directly in kinematical space? Okay, so now this is actually pretty cool. So what are the amplitudes directly in kinematical space? So they should again be a differential form. But now in kinematical space, it's much easier even to think about what they should be. Like let's say we're just talking about gluon amplitudes, and we want to combine all gluon amplitudes together into one nice object of different helicities. Now, I stressed to you that supersymmetry allows you to do that. That naively, when I have the individual helicity components, they're all different guys, but supersymmetry tells you how to combine them all together. Also, polarization vectors and Feynman diagrams glue everything together, but in this horrible, at least from our point of view, this horrible non-gauge invariant crappy thing. But the invariant content, it seems like there's no way to put everything together other than if you have a symmetry that relates everyone. But that's not true anymore once you have this idea you're looking for a differential form instead. Okay, so how can I make a differential form out of amplitudes? We can do this in the standard model today. Okay, we can actually start thinking about the scattering amplitudes in the standard model of differential forms in kinematical space and start exploring what their properties are. Okay, so what you do is you make a form where if you have a positive helicity gluon, okay, how do I eat up its weight? I make a 2 form out of it by, let's say this is for gluon 1, by wedging it with d squared lambda. That eats up the helicity weight. Okay, and then if it's got a minus ball, I wedge with d squared lambda tilde. And I do that for all of them. Okay? So in this way, if you have scattering amplitudes from massless particles in 4 dimensions, immediately it's associated with a form that lives on kinematical space that combines them all together. Now, if you apply that logic to n equals 4 super Yang-Mills, you will get the form we know and love that takes care of all the supersymmetry. But we don't have to do it. We can do it just for gluons. We can do it for any theory. Okay? I didn't talk in the course about how we expend spinor helicity variables to massive particles, but it's essentially trivial exercise to extend these things to massive particles. And then you can build these forms for massive particles too. So the idea that amplitude should be thought of as forms and that that's a way of unifying them all into one object is a very general one, and you can, as I said, apply it for massless particles and massive particles of the standard model right away. What you learn by doing this exercise, what you might learn by doing this exercise is just as we saw for n equals 4 super Yang-Mills. Once you have a form, you can ask questions that you can't ask when you have a function. When you have a form, you can talk about residues. You can talk about patterns of residues and so on. That's not something you can do when you just have a function. Okay? And for n equals 4 super Yang-Mills, that form is what reveals the underlying geometry of the amplitahedron thought of in momentum twistor space, and one can explore questions about what the cousins of those forms look like in totally non-supersymmetric series. While I'm at it, going back to n equals 4, I want to mention another connection. That's the kind of where the much of the subject started to begin with. There's a connection. So this is an existing connection to twistor string theory. And you don't need to know anything about twistor string theory, because I'm just going to give you the complete definition of what it is in a second from the Grassmannian point of view. Remember that we had this idea that we wanted to integrate over the Grassmannian, just going back to lambda tilde space again, not momentum twistor space, that we're going to integrate over the Grassmannian with some measure of the thing that imposed the condition that C contains lambda and is orthogonal to lambda tilde. And what we've been focusing on is, or what we focused on when we talked about on-shell diagrams and so on, was that we have this form with cyclic minors, and that we have to take enough residues so that in the end we had a 2n minus 4-dimensional integral left. So we had some sort of 2n minus, we wanted to integrate over a 2 minus 4-dimensional cell of g plus kn. So in other words, we have to do the rest of the integrals on residues to get to a 2n minus 4-dimensional, so let me put residue here, to get to a 2n minus 4-dimensional cell of the Grassmannian. And that's because this delta function in the end was a 2n minus 4-dimensional delta function. OK? But there's another thing that you could do, which is to just find another form to integrate on the Grassmannian. Why not? Let's see, is there another form we can integrate on the Grassmannian that's naturally 2n minus 4-dimensional? Now, 2n minus 4 is a number that we've gotten used to in this course. 2n minus 4 is a dimensionality of g2n, right? So 2n minus 4 is the number of variables of n 2 vectors modulo GL2. But I want to integrate something in gkn. Okay, but there's the following very beautiful and simple map that's in projective geometry 101 courses, algebraic geometry 101 courses. There's something known as the Veronese map. So if I take a 2-vector AB, okay, the point of the Veronese map is that you can take AB to a k vector that looks like a to the k minus 1, a to the k minus 2b, blah, blah, b to the k minus 1. Let me call it k. Is that clear? So I could take, for example, sorry, I want to do k minus 1. For example, I can take ab to a squared, ab, and b squared. That's a way to make a 2-vector into a 3-vector. And what's the obvious nice property of this? The obvious nice property of this is that if you do a 2-by-2 linear transformation on AB, that's some k by k linear transformation on the map. Okay, so that's why it's a canonical way to map something from P1 into Pk minus 1. Okay? Is that clear? With the natural action of the GL2 acting on it. Okay, so with this map, what you can do is, if you give me n 2-dimensional vectors, sigma 1 through sigma n, then I can map them into a k by n matrix, which I call C Veronese of sigma, which is just this sigma Veronese of 1 up to sigma Veronese of n. Is that clear? OK? And so here's an interesting thing that you can try and do once you're in this Grassmannian state of mind. You somehow want to find some 2n minus 4-dimensional place to do an integral over the Grassmannian. It should care about ordering, should care about all these other things. So why not do this integral? This integral d squared sigma 1 up to d squared sigma n. And the form that we know and love on positive g2n in terms of the sigma, so modulo GL2. So this is a 2n minus 4 form. And then we'll do delta C Veronese of sigma and lambda. So in other words, we're going to integrate over the Grassmannian, but we're going to integrate over this subvariety in the Grassmannian that's the Veronese, the image of G2n under the Veronese map. OK? This is twistor string theory. Okay, So this is the formula for scattering amplitudes that Witten wrote down back in 2003 that sort of kicked off the modern revival of this whole subject. And notice I've not said anything about topological A model, blah, 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 blah. You know, all the motivation stuff is sort of gone. And in this Grassmannian view of the world, it just happens to be a particularly natural way of finding a subvariety to integrate over in the Grassmannian. Okay? Now, let me just give you an inkling of an idea of how this works. So let's say I want to see what this integral looks like for k equals, so first for k equals 2, there's nothing to do, right? For k equals 2, the Veronese map is the same as sigma, so this just says c is the same as sigma, and we're back to what we're doing before, right? Because this is just saying, this is just our Park-Taylor formula, all the stuff we were doing before. Okay? So it's interesting for the first time at k equals 3, and let's actually do k equals 3 and n equals 6. And so you see, the Veronese map is telling me, let me rescale the top component to be 1, okay, just for convenience. The Veronese map is telling me that the C matrix looks like 1, like sigma 1 squared, 1 sigma 2 squared, up to 1 sigma 6 squared, let's say, if I'm doing k equals 3, n equals 6, right? So that's what C Veronese of sigma looks like. It's an 8-dimensional space. I still have an SL2 that I'm modding out by the sigma, so it's an 8-dimensional space. G36 is 9-dimensional, and so I could think of this actually as an integral over the entire Grassmannian, but with some delta function, or better yet, a pole, restricting me to this Veronese subspace. Okay? Now, this was one of the problems I gave you on a problem set. Actually, we even talked about it in the class. What condition does this 3 by 6 matrix have to satisfy in order to ensure that it's of this form? Now, what does being of this form mean? It means that all the 6 points that I can think of as the columns of the matrix actually lie in a conic. Right? Because they all have to look like 1 sigma squared. So literally there's a parabola here. But if more projectively invariantly, if I do an SL2 transformation, it's any old conic. So this is actually the condition that 6 points lie in a conic. And that was one of the things that Pascal solved for us in the 1600s, and which we can say in projective language. For 6 points, 1, 2, 3, 4, 5, 6 to be on a conic, we have to have the following invariant, 1, 2, 3, 4, 5, 6 equals 0, where this is 1, 2, 3, 3, 4, 5, 5, 6, 1, 1, 2, 4, 6, minus 2, 3, 4, 4, 5, 6, 6, 1, 2, 3, 5, 1. So this is a pretty non-trivial statement. But it's on one of your problem sets that if you want to check if 6 points are on a conic, this quartic in the minors has got to equal 0. OK, so whatever this integral is, it looks something like this. It looks like an integral. It looks like an integral over all of G36. And it has to have a factor we'd normally call a delta function, but let's write it as a pole instead, because everything we're doing is like that. That's this 1 over S1, 2, 3, 4, 5, 6. So let me write it out. 1, 2, 3, 3, 4, 5, 5, 6, 1, 2, 4, 6, minus 2, 3, 4, 4, 5, 6, 6, 1, 2, 3, 5, 1. So I have to impose this as a pole. OK, so I'm going to do a residue on this pole. So I really have d3 times 6 c mod gl3. And now that something has got to make up for some weights and gives me, and really I want this particular measure. Okay, so this is really a straightforward exercise in computing a Jacobian. I won't tell you how to, I won't go through it in detail, but it's just I'm doing nothing other than just computing a Jacobian to go from these variables to the C variables in the Veronese form, and taking up the Jacobian from imposing that delta function or the pole. And the Jacobian ends up being, just to write out the answer, something very simple, 135 over 1, 2, 3, 3, 4, 5, 5, 6, 1. And you might say, oh, wait a minute, that looks kind of asymmetrical. Why is 135 special and not 2, 4, 6? Well, but remember, this is all in the support of this pole. Okay, so it doesn't matter which one you choose. On the support of this pole, you get the same answer. Okay? So in other words, this is what the integral over the Veronese subvariety looks like, thought of as an integral over the entire Grassmannian. And I still have this delta of C and lambda in front of everything. Okay? As usual. Now, as you remember, this is 2n minus 4 is now 8-dimensional. So this delta function is going to eat up 8 of the 9 integrals. And I just have a 1-dimensional integral left. And it's a 1-dimensional integral that has to enclose the poles of this weirdo object. There's some complicated polynomial in the one variable that is left. So let's think about what this final integral looks like. So I have a final integral in this one last variable that I have left. There is some region where there's a bunch of poles associated with S. And I'm supposed to surround all those poles. Okay, I'm supposed to sum over all the residues of what I get when I set S to 0. And then I have some other poles, in principle, associated with these other minors vanishing. Okay, some other poles. From when 1, 2, 3 goes to 0, 3, 4, 5 goes to 0, and 5, 6, 1 goes to 0. OK, and this was the twistor string formula. And you were supposed to sum over this complicated set of roots of this equation. And if you did it, magically people found that you got the right answer. Okay, but now we can understand better what's going on. I'm supposed to sum over all of these residues. But I can use Cochise theorem to say that it's instead the sum over all of these residues, where I surround these guys instead. And now look at what happens. On the residue where, like, let's say 1, 2, 3 goes to 0, this term is gone, right? The 1, 3, 5 cancels the 1, 3, 5. So what is that residue? This residue where 3, 5, on the residue where 3, 4, 5 goes to 0, it's the same as the residue of 1 over 1, 2, 3, 2, 3, 4, 5, 6, 1. That's our cyclic minor form. Okay, so in the positive Grassmannian, we were supposed to sum over particular residues of the form of cyclic minors to get the right answer. Which particular sum? The one where, if you remember, 1, 2, 3 goes to 0, 3, 4, 5 goes to 0, and 5, 6, 1 goes to 0. Okay? And those are exactly the ones that we learned that we're supposed to do by doing a contour deformation on what we're instructed to do by twistor string theory. Okay, so there's a relation between the twistor string and the Grassmannian formula just by a contour deformation. Right? The amplitahedron, now we understand, tells us why we're gluing these particular residues together. And it would be fascinating to find a direct link between the amplitahedron and momentum twistor space and the twistor string. And it's a non-trivial map, you see, because it's not like the twistor string immediately knows about the Grassmannian. It also doesn't know about the Yangian. It doesn't know about all kinds of other things. But it has this beautiful picture purely in the Grassmannian now of why we're gluing residues together. It's a purely Grassmannian picture for what the amplitude is, that in this way of thinking about things, we can relate to the positive Grassmannian world and the sum over the sum over residues of the positive Grassmannian. Now, part of the reason why the on-shell diagram, BCFW, everything else I've told you about in this course program went a lot further than the twistor string is that this is just incredibly hard to work with. in this very simple example, you definitely don't want to take literally the formula and sum over these roots. It's already horrendously complicated for this simple case. And already in the simple case, we see that the point was that it could be deformed back to something we could easily compute and understand. Nonetheless, there's something remarkable about it. There's something remarkable the fact that there's a kind of 2n minus 4-dimensional kind of string worldsheet that we're integrating over. It's rather different than the ordinary open string worldsheet, which is n minus 3-dimensional, right? This is a more, the twistor string worldsheet is really the positive Riemannian, positive G2n. The open string worldsheet integral is really endpoints on P1, not quite the same thing. It's taking out the overall scaling of all the columns, a topic I'll come back to in my 3 lectures, okay? In my 3 bonus lectures. But I bring this up only to say that there's even other things in this world of ideas that have not yet been fully connected, even at tree level. And of course, there's not much of a clue of what's going on at loop level in the world of the twistor string. But I think if we make a connection at tree level, a proper connection at tree level between the momentum amplitude, which is just starting to be understood, and the twistor string, that might tell us something about how we're supposed to proceed from there. Okay, so those are just some of the open problems. Let me just say one thing before Matt kicks us out and kills me. Everything that we've talked about, for the past month and a half or so, has been about n equals 4 super Yang-Mills. And in the bonus lectures, we'll switch gears and talk about just phi cube theory or the pions, the nonlinear sigma model, no supersymmetry, et cetera. But sticking with gluons, we can go to less supersymmetry. And I just want to say a few things. Absolutely nothing stops us from studying on-shell diagrams for non-supersymmetric theories. And if we study them, everything that I told you about gluing them together, Riemannian representation for the 3 particle amplitudes, all those things are exactly the same for any theory. In particular, for any planar theory, every on-shell diagram is always associated with exactly the same structure in the positive Riemannian we've been talking about. Okay, so the connection between the positive Riemannian and 4-dimensional scattering amplitudes is there really for any planar theory. Okay? There's also a connection beyond the planar limit. It's just not the positive Riemannian. There are other structures in the Riemannian. It's still a general fact that in order to glue together on-shell diagrams, the best way of doing it is to associate them with these little G13s and G23s and do the amalgamation that you get. And if the diagrams are non-planar, you'll get another structure in the Riemannian. Not the positive Riemannian, but you'll get some other structure in the Riemannian that's worth looking at. But even sticking with planar theories, if we have less supersymmetry, the fascinating thing is that all this delta, C, and lambda stuff is exactly the same. We still have the d log of all these edge variables, just as before. And we have one more factor. There's some interesting Jacobian factor, which is sitting there out in front of the whole thing. It's literally raised to the power of n minus 4, where n is a number of supersymmetries. Okay? Now, the interesting thing is that this j depends on where you are in the Riemannian, but it literally does not intersect the positive Riemannian. So in other words, where j goes to 0 does not intersect the positive Riemannian. And there's lots of indications that the world where j goes to 0 controls the ultraviolet. That's the major thing that's missing when we go to less supersymmetry. There's the ultraviolet, there's ultraviolet logarithms, running, the RG, all of those things. Those things that I've stressed maybe early on this course, that to my mind is where the real challenge lies in connecting on-shell physics in some deep way to the real world. Because that's the place where the standard way of thinking about quantum field theory that Wilson gave us is at its most powerful, right? Not for questions about scattering amplitudes that are sort of oddball questions from the perspective of a Wilsonian effective field theorist, but the RG and organizing physics by scale and all this Euclidean stuff. If we're really going to think we're doing something, we had better be able to attack the enemy on its home turf. And in this case, is try to find some kind of on-shell understanding of the renormalization group and the ultraviolet and all of that stuff. All I can tell you, essentially nothing has been done on this subject. All I can tell you is that there's this place in the Riemannian which naturally is associated with that. It is not the positive Riemannian, but somehow, quite uniquely, it doesn't touch the positive Riemannian. The kind of the decoupling between the UV and the IR that we see in space-time is also seen very cleanly in the Grassmannian. There's this other locus of something interesting happening, and that locus is very clearly associated with ultraviolet physics, thought of from an on-shell perspective. That's the novelty. How do we think about UV things that are naively Euclidean and all this? How do we think about them in a non-shell perspective? And there's a region in the Grassmannian sitting there, trying to be to be explored to see if it gives us some picture for what is going on. All right, yeah.
So that's for quantum field theory, right?
Yeah.
For quantum gravity, is there anything different you can say? Perhaps that region does intersect, because in quantum gravity, there's a connection between UV and I.
Yeah, well, so everything here was a perturbative. So I think all the connections that we know, and all thing about the on-shell diagrams is perturbative. And actually, I just want to say, just in 30 seconds, but I'll say more about it since I have a few bonus lectures. But since we're in this neighborhood, just going back to the twistor string, here we have some interesting 2n minus 4-dimensional integral. There's another beautiful natural 2n minus 4-dimensional space that we can be thinking about in connection to scattering amplitudes, and that's the celestial sphere. Okay? So this is something, again, that Andy and Monica and a lot of people around here have been thinking about. But there's strong resonance between, at least kinematical resonance between a number of these ideas and the transforms of amplitude to the celestial sphere. But anyway, before we're mauled by the oncoming horde, let's leave it at that. And I might say a little bit more about it if I have a fourth bonus lecture. Okay. All right. Thanks a lot, guys.